let me introduce you to quantum mechanics, a concept where normal math and physics don't work. Weird, right? Yeah, even after hours of research, I don't really get it either. Spend the next few minutes with me while I briefly discuss the timeline of quantum mechanics. It all started in the 1890s when people were puzzled by the light emitted from heating objects. Classical physics said a hot object should give off an infinite amount of ultraviolet light, but no experiment ever conducted actually showed that. This was the ultraviolet catastrophe and is what led towards the birth of quantum mechanics. Around the 1900s, a research facility in Berlin did experiments using a black-body radiator. Max Planck analyzed some of their data, but classical physics couldn't explain what happened at high frequencies. He proposed that energy is not emitted continuously, but in tiny specific packets called quanta. Energy wasn't a stream. It existed in small pieces with specific amounts. Planck solved the ultraviolet catastrophe. Meanwhile, Philip Leonard was experimenting with a gold leaf electroscope. It worked by electrically charging two golden leaves which pushed them apart. He found when he shone high-frequency light on it, the leaves would close, but lower-frequency lights did nothing. This phenomenon was the photoelectric effect. Come around 1905, big brain Albert Einstein explains the photoelectric effect. He reimagined light as particles with discrete packets of energy, photons. It showed that light had a specific amount of energy based on its frequency. This is why red light did not affect the leaves in Leonard's experiment, because it didn't have enough energy to release the electrons. Einstein explained the photoelectric effect, but now it raised questions. Was light really a wave or a particle? With all the new discoveries, Niels Bohr re-examined the atom and wondered if electrons did orbit around the nucleus. How did they not lose energy? In 1913, using Einstein and Planck's ideas, he found that each electron had their own individual orbit based on its restricted energy. To change its energy level, it would absorb photons, making it jump orbits, producing certain colors of light. This was a big step towards quantum mechanics. In 1924, Louis de Broglie had a revolutionary theory. If light could behave as particles, could electrons behave as waves? He created a crazy hypothesis called the de Broglie wavelength, which said anything could behave as a wave or particle depending on the experiment. Not even a year later, de Broglie's wavelength was actually proven by scientists Clinton Davison and Lester Germer when they fired electrons at a nickel crystal and found that the electrons formed a diffraction pattern just like a wave would. This proved de Broglie's hypothesis and supported the idea of superposition and wave-particle duality, which in short means electrons can exist as waves or particles. In 1925, Werner Heisenberg realized that classical physics did not work in the quantum world because value could not be predicted with formulas. Rather, it was based on probabilities. So he created matrix mechanics, which used large tables of numbers to punch out probabilities. He also found that in the quantum world, AB did not equal BA. This was the uncertainty principle that showed position and momentum could not be known simultaneously. This was the first foundation of quantum mechanics. In 1926, Erwin Schrödinger hated the randomness of matrix mechanics and created an equation called wave functions, which stated particles did not exist in exact points but were spread across like waves. Turns out his deterministic view was still wrong, and his wave function actually complemented the probabilistic view of quantum mechanics. In 1927, Heisenberg and Schrödinger determined that quantum mechanics was in fact probabilistic. They concluded that in the quantum world, the observer was at the center. A particle's location could not be found until observed. This also led to the principle of complementarity, which states particles behave as waves or particles but cannot show both at the same time. This was the Copenhagen interpretation. In 1928, Paul Dirac attempted to combine quantum mechanics with special relativity, a huge feat. He created Dirac's equation and succeeded in describing an electron's quantum movement like spin, but his equation also predicted a new kind of matter, antimatter. It was a particle that was similar to an electron but with a positive charge. His theoretical particle was then found to be real in 1932 when Carl Anderson discovered particles similar to electrons but with a positive charge while working on cosmic rays. The 1930s brought along a solid foundation for quantum mechanics. Years of research from multiple scientists were used to form the quantum field theory. This theory stated that particles weren't tiny balls but were excitations of fields. What that means, I don't know, but by thinking of them as this, it helped combine quantum mechanics and special relativity into a unified framework for the quantum world. The decades after, scientists started refining their newfound information and even started applying them. The 1990s is when scientists started using quantum mechanics in technology, specifically quantum computing. Using quantum mechanical principles like superposition and entanglement, a computer's ability to problem solve became exponentially faster. Nowadays, quantum mechanics is applied to semiconductors, MRI machines, and quantum computers. It's also become popular in huge companies to create their own quantum computers. An example would be Google's Willow, which is a 105 qubit quantum chip. Thanks for listening to my brief timeline. I hope my fellow classmates will further explain some of these topics.